there we go. Yeah, sorry for the short delay. My computer decided it was a good time to update right when I was scrambling to get here from my other class, so so not the best timing. So last time we covered kind of the force balances for particle sedimentation. Talked about how it's a lot like skydiving. The particles are going to be falling through the water. Unlike skydiving, they reach a terminal velocity very, very quickly. Skydiving might take, half a minute or something. And that's largely due to the difference in mass and buoyancy, and viscosity of the liquid, right? So if we stop and think about what's all determining that sedimentation velocity, we have several constants. The difference between densities between the solid and the liquid, and the drag force shows up in terms of viscosity and the diameter of the particle. Now, one thing that we could stop and think about before we even talk about designing a reactor, because that's what we'll talk about today, and as we move forward to the next lectures, how to improve sedimentation, we look at how to improve this number. How to improve how fast these particles are falling through the water. That's going to tell us a lot about how big of a reactor we need. That's going to tell us a lot about what kind of particles we can remove. So if we can change the density, the viscosity of water, that could be a thing, right? If we see on the denominator here, if we decrease the viscosity, that'll increase the settling velocity. So particles will settle faster through water than through honey. And you kind of know that already. Didn't have to tell you. We could make the particles heavier, perhaps, or more dense, rather. That would have some impact. But probably the easiest thing to do would be to go to Jupiter. No. So we could maybe change the gravity, right? But the easiest thing to do would be to change the particle size, especially because that's to a square power, right? So because we are squaring the diameter, and that is affecting our system, that's the best thing we can do in terms of the most outcome, the best increase of our sedimentation velocity given some change in the system. So changing the particle diameter, making them bigger particles, will inherently make our stuff settle faster, because that's on the numerator here to the square power. So we'll come back to that, but just kind of giving you a little foresight into thinking about how are we designing this, how are we helping our designs? Well, most of it's going to be manipulating that particle size. And typically, the way we'll do that is try to get particles to stick together to form larger particles. Okay, so now that we have some sedimentation velocity, what does this look like in practice? How do we do it? How do we design a system? Well, if we take a look at water treatment systems, we will often see these large circular basins. Sometimes we'll see long rectangular basins, and not every single circular one is going to be a sedimentation chamber, but many of them will be. These are, in wastewater, we tend to call them clarifiers. We are clarifying the water, making it more clear. In drinking water context, we usually just simply call it a sedimentation basin. Sometimes maybe clarifier. It doesn't really matter if we use a horizontal, like linear one, or a radial one. The deal is, either way, we can map how particles are settling as a function of distance from where they started. So at the very simple case, we have particles, water flowing in this direction, and particles are settling over time as water flows. So if this is our flow rate, we want the particles to reach the bottom, because as soon as they touch the bottom, we consider them removed. Typically, we will be collecting water from the top, or kind of near the top in general as part of that. But as soon as they stick on the bottom, they're going to stick to other particles. They are removed for the purpose of our reactor. So that means all we have to do is get a particle to reach the bottom before the water exits. So we have some velocity of water going through, and we have the particle velocity going down, right? So we have Vs for our particle, and the the slowest particle that we can possibly remove is the one that follows the path that is diagonal through this rectangle. So that particle is removed. Anything slower is not. Okay, so we can define something about our sedimentation based on that simple principle. If it reaches the bottom, it's gone, and it's going to do so based on the velocity downwards compared to the sideways velocity through the reactor, right? So it's going to be very simple physics driving this in that sense. We can get a horizontal velocity if we want to. We'll just have to take that flow rate and divide it by the total area that it's flowing over. We're going to do that, but we're going to leave it kind of implicit in the other ways we calculate it. So we'll get to those specific calculations in just a moment, but what I want to show you is even if we did have a circular reactor, or I'm going to make a little more space here. So even if we did have one of these circular chambers, cylindrical maybe, the way we can look at this is having any cross section in here would be like drawing one radii. So the water in these circular sedimentation chambers is going to flow from the middle, radially outward to the edge of the reactor and be collected. Okay, so that's how they're going to flow. So it doesn't really matter what direction we flow it. The waters, we can then take a cross section for that particular flow, and I might as well make this a little more clear. And then we take that cross section here, turns out to be a rectangle, right? And then we have water flowing across, and it's the same exact rectangle as if we had just a rectangular sedimentation chamber, because this is a cross section we're looking from the side at this. So in this case, this is the height, and then we have a length, and then we could also think about the width. So in this case, this would be height, this would be the length, and in the circular one, we don't have a width, but we have an area is pi r squared, right? Or we could do diameter. In this one that's shown on the upper right, this would be our length going across, and we'd have the width here, and then we can imagine this is a top-down view instead of cross-section, so downwards would be, into the picture would be the depth or the height. Does that make sense, how I'm visualizing this? Okay, so it doesn't really matter the type of sedimentation chamber. We're going to take a cross-section and watch water flow horizontally through that cross-section, and the particles are going to be traveling downwards. So that's the schematic, and that's how we're going to understand these. And of course, we could imagine this in 3 dimensions like that. This also means our area for a rectangular is going to be length times width, right? Pretty obvious stuff, just making sure it's very clear because we need to call each of those pieces here in a moment. Okay, so let's consider a reactor with some total height, and then the height of a given particle being hp. So if we put a particle right here as it enters, then that height is hp, whereas the total height would be this guy. Now, for most of the stuff we want to do, we're going to set the height of the particle at the top because that's going to be the hardest one to remove. But before we go there, I just want to show real quick, if we started with a particle there, the slowest one from there that could be removed would have a sedimentation velocity taking it on that trajectory. Now, if we had that same size particle, so same speed, but it started at the top, it will have the same looking trajectory, but it's going to escape, right? It's going to make it out of the reactor, and we failed to sediment it and remove it. So what we can see here is that sometimes we'll have a condition where we get partial removal. What we want is total removal, or at least to be designing with that in mind. So I'm going to say for a moment for complete removal, we should set HP equal to the total height. And I guess I'll use the lowercase h here. So if we set that equal to HP, then we're aiming for total removal. So if this is now the height of the particle, that's how we'll design our reactor to say, okay, the worst case scenario, the particle's at the very top of the water and we need to get it to the bottom. If we can achieve that with the one at the top, we will achieve all of the particles removed. Okay, so then how do we think about, or how do we decide what is that speed at which it has to be removed? So in this case, we're talking about this guy reaching the end and being removed. So what we can do is we can say that's some distance that the particle has to travel downwards, and we're going to have some time with which it has to do so. So if we say we have to travel some distance, and we need to do that over some time, that's a velocity term, right? Distance per time. So what we'll say is that's going to be we need to set that equal, we need to figure out an arrangement such that this is the settling velocity of our particle. If we get our settling velocity, Vs, equal to the distance divided by the time that we have to let it settle, we're good. In fact, we could just slow down our flow potentially until it settles. That's one possibility. Now, in practice, we don't typically like to slow down our flow in a water or wastewater treatment system because we need to meet some flow demand. We don't want to let that wastewater pile up, and we don't want to let the distribution system go dry, right? Neither of those are options, really. So we can't actually slow down the system, but theoretically we could. Maybe if we had extra capacity or something like that. So that gives you some idea of how we're going to manipulate our system here, is designing distance over time to match how fast the particle settles. Now, time would be hydraulic residence time. How long is the water in the system, right? So this is going to be the distance it has to travel is the height of the reactor. And at this point, I'm just going to call it h for the height of the reactor divided by theta. Theta being our hydraulic residence time, which is the volume over the flow rate. Right, so we could rewrite this, say h is, the Vs is equal to, this is a bad way to write this. What we need, sorry, I'm going to backtrack a little, say we need to achieve some distance over some time. So I was over here, the Vs is going to be h over theta, which is saying h over v over q. At this point, the v is starting to tell us something about the reactor dimensions itself. So if we use the h and the v both relate to the reactor dimensions. So assuming we can't really mess with q, well, what can we mess with then is the reactor dimensions. All right, so as we design our reactor, what we're going to say is we want our reactor to be able to sediment these particular particles. And if we write this out a little differently, we can say this is h divided by the area times the height of our reactor divided by q. So we'll go ahead and divide that and say this is going to be equal to h times q divided by the area of the basin, I'll put a b there for the basin, times h. So the h's will cancel, and we will get a term that says q divided by the area of the basin. So what we've just done is somehow done some algebraic magic to get rid of the height altogether, which is kind of funny because you think of like, how long is it going to take for this thing to settle? Its height's not even, like where it starts, and the height of the system is not even a factor in a way. It's technically accounted for given the flow rate and everything. That flow is going, if this is a rectangular system, that flow is going over this area of this basin, right? So given this is length, this is width, the area in this case is length times width. Of course, if it was circular, we'd use the area of a circle. Okay. The other thing I want to say here is when we set VS, when we're designing for a particular sedimentation velocity that our particles are, and we set that equal to this, we can actually better describe that to say this is the design velocity. So V naught is our design velocity. And when the VS is at least equal to, if not greater than the design velocity, then we're removing all the particles. That's the way we can describe that. So any VS, so VS can change, right? If we use a different particle, that's a new VS. If we have any VS that is equal to or greater than or equal to V naught, then all of those particular particles at that speed are removed. Okay, and that just happens because they're reaching the bottom, right? It's fine if they reach it faster, but under the condition of V naught, that standard or that design criteria, that's exactly when they just barely are removed. All right, any questions on that? Does that make sense so far? Okay, so this is one of the few equations I'd like you to just memorize, or remember how to derive. It's quite simple. The V naught is Q over AB. I don't think I put it on your formula sheet. So the derivation here, you can think of it as simply as, all right, it's got to go some height, and we have our hydraulic residence time. You should be able to calculate everything from there. So this is just warning you that's a simple one, but one that you should remember. Okay, so just to elaborate a little bit and to make it more clear, I have that all written out here. VS is the specific to a particle. So a different particle has a different VS. V naught is specific to our reactor. So once we've designed it, that's just what it is. And then we can make some comparison. And we might also call it critical settling velocity. Okay, so if this line is shows what happens with V naught, we talked already that maybe we have a particle down here that is fine. Maybe we have a particle that looks like this, some VS, I'll say VS1. We might have a VS1 particle that starts down here at that same VS1, and it's removed, right? So it's not exactly clear how many of those will be removed, unless we draw it such that we have this also being the VS1. Then maybe we can find some portion of particles that are removed in this system. So we have however many particles were in this area, those VS1 particles are all removed because at the top of that section, they were removed. And we can end up finding that with a bit of math we'll look at in the next slide. So all this is to kind of say, we could also have VS2. Maybe it's just going even faster. Those are definitely all removed, right? It's very, very intuitive here. I just want to make sure it's clear. And again, this could be a circular reactor. We're just taking the cross-section and see what happens in that cross-section. Okay. So we already derived this equation. I think this is just a little more space. And I think I've got the portion of stuff removed on the next slide, so I'm going to just skip over this because I think I've already said that. Oh, never mind. I'm going to stop here. Maybe I'll say this again with another slide. I thought I had a slide for it. We can describe the portion of particles removed. So in that example where not all particles are removed here for a given Vs, right? If this is the same line, same velocity here, we can actually find the portion of water that escapes. This is the those are the particles escaping, right? And so, well, actually, let me say that. I think it's easier if I draw it on the other side. So this is the portion that are removed. So I said that backwards a moment ago. We see that because all of those reach the bottom. So then this is the portion escaping. So we can actually derive a percentage that are removed. So we'll say removal percentage. And that would be equal to some ratio between the Vs and the V naught. So if the Vs is slower than V naught, we're only going to have a portion of the particles removed. So this ratio then is simply Vs divided by V naught times 100%, which it ends up being pretty intuitive. If your speed is half of what it needs to be, then the particles starting halfway up the height are going to be removed. Anything further than that won't be. So it's actually quite intuitive as well. Now, one thing that you could get wrong is you could theoretically do this calculation wrong or get the thing backwards and say, oh, we've got 120% removal. But hopefully you recognize that's not physically possible. You can't create particles just to remove them, to say I had more than 100% of them, more than all of them removed. That just doesn't work, right? So check yourself with that. Make sure you're not giving me a value of 200% particle removal. And maybe I give you a number where Vs is larger than V naught. Still, you can't have more than 100%, right? That's just all of them, which is, again, going back to what we were talking about earlier. But this is another equation we can use. If you want to, you can take a look at the height traveled and relate that to the escape here. And we can correlate that to, if Vs over V naught, this would be, let's say, the height of the particle over theta and the height of the reactor over theta. So you can also relate it in that sense of how far did it travel in that time and make that comparison. So you can dig into it a little deeper if you want, or relate it in another way. But that's kind of how you see the height here showing up, whereas this part would be the HP of the one removed. So, okay. And like I said, I think I have a slide that lays all this out in text as well, but just got ahead of myself here. Does that make sense, though? Any questions? All right, so let's give it a shot and solve this example problem. It is silt removal in a clarifier. So a drinking water treatment plant uses a circular sedimentation basin to treat 3 million gallons per day of river water. It gives us the abbreviation there and gives us a way to relate that to cubic meters per second. After a storm occurs upstream, the river often carries 0.01 millimeter silt particles. So that's a diameter they're giving us. If you see that, they give us some size particles. That's safe to assume, unless it specifies otherwise, that's a diameter. So diameter of those particles. With an average density of 2.2 grams per centimeter cubed. The silt must be removed before the water can be used. The plant's clarifier is 3.5 meters deep and 21 meters in diameter. The water is 15 Celsius. So the question is, A, what is the hydraulic detention time of the clarifier? So that's asking for theta. And B, will the clarifier remove all of the silt particles before or from the river water? So is it going to work? So I'm going to write up a couple equations here to remind you, but take 5-10 minutes. Feel free to work together and see if you can come to an answer on this. And maybe in 5 minutes or so, I'll start talking you through a few steps. Yeah. So good question. So the homework solutions, I can probably go ahead and post those later today or when I post the. Normally, what I will do, I could go ahead and post those, but normally what I'll do is I'll go through all of homework 1 and 2 as exam review and post them at that point. But if you're interested in having them earlier, I can probably post solutions from last time. Yeah. So, okay. So, all right. Go ahead, please work together if you'd like to. Remind you some equations here. All right, how you feeling about it? Okay. I think yeah. Q is the flow rate that was given in terms of the plant treating some amount of river water. So that's the 3 mgd here. So it's mgd stands for millions of gallons per day. And then it gives us an exchange or we could look up the gallons per day and convert that to meters, cubic meters in seconds, but it just gives all that conversion to us right here. And so what I did was I said Q, and I did this in Excel, I'll show you in a moment, is 3 times that value because we're doing 3 mgd. All right, so I think I took care of most of the tricky stuff. The one last part might be remembering when you look up the mu here, that's 1.139, but checking the units, that's times 10 to the minus third kilograms per meter second, right? So 10 to the minus 3 kilograms per meter per second. Okay, so what you'll notice is I already I solved for part A using that Q there. The 3 times 0.0438 gave us that 0.1314 cubic meters per second. I also had to calculate for V, and this is a circular sedimentation basin, so something like that where we have area of a circle there and a height. Multiply those two together, so that should be the height times that area. It's the volume of a cylinder. That's where we're getting this calculation here. And so what I did was I said 3.5 meters tall times pi r squared. I just went ahead and took 21 divided by that by 2. That's 10.5 meters. Square all that, and I just did it that way. So that gives us a volume of 1,212 cubic meters. So with that and with the flow rate, we have a hydraulic resonance time of 9,226 seconds. Now, I went ahead and left it in seconds because I figured we're probably going to be using seconds. Typically, that's what we'll do. It's quite a large number, so it kind of feels funny right now, but I'm just going to leave it like that for the moment. You could convert it to minutes or hours or something and might feel a little more tangibly reasonable there. Okay, so then part B, to set it up, we need to use the settling velocity equation. Gave that to you here, reminded you about that. That's G, the acceleration due to gravity, times the difference in density from the water to the particle, and times the diameter of the particle squared divided by 18 times that viscosity. So the diameter of the particle is 0.01 millimeters. If we calculate that, that should be 10 to the minus 5th meters, or 10 times 10 to the minus 6, if we want to do the conversions that way. So we have that. That'll be the particle squared. The density of the particle was given to us as 2.2 grams per centimeter cubed. So we need to do a conversion there. I went ahead and wrote it out for you instead of just using cheat codes, and said that'll be 1 kilogram divided by, or per every 1,000 grams. And then we can multiply that by 100 centimeters in every meter, and then cube each of those, right? So we could even write this as, we're just going to say there's 100 centimeters in every meter, and then cube both the top and the bottom of that, right? That's the technically correct way to do that conversion, so you make sure you're cubing the factor that you're exchanging. So that would give us 2,200 kilograms in every cubic meter for the density of the particle. Density of the water was the lookup. That's 999.1 kilograms per cubic meter. With that, and with the dynamic viscosity at 1.139 times 10 to the minus third, everything should be in place at that point to calculate the sedimentation velocity, which I will do with you here. Actually, I've already done. So I've got all those pieces, and we're going to get a value in meters per second. That should be 5.75 times 10 to the minus 5th meters per second. And what you'll notice is I wrote in the acceleration due to gravity. I did the density of the particle minus the density of the water, times that 10 to the minus fifth squared that, all that divided by 18 times that dynamic viscosity. So I just put that in Excel. You could do that in your calculator. So that should be 5.75 for the value of Vs. Now this number should be a small one because we're talking about meters per second and a very small particle. It's not going to be going multiple meters in 1 second. Right? That'd be extraordinarily fast, like probably faster than a bowling ball would go. So we're not going to be that fast. So it makes sense that this is a 10 to the minus something number, usually 5, 6 range, okay, for particles that we might settle. Maybe sand goes 10 to the minus 4. All right, so that doesn't quite answer the question just yet, but we're very close. So I think I've got more space to find that last answer. Of course, we did answer A, so we'll continue here and say, all right, is that going to remove them all? So here's the question. Question really is whether or not Vs is greater than or equal to V naught. That's the variable way to ask that question, which is probably a useful thing for you to do sometimes, right? Take a look at the question and see if you can write that question in an equation form. Is this equal to that, right? And so that's what I've done here. Is Vs faster than the design velocity that this system is made for? So we have to find the design velocity, V naught, and we just learned this a little bit ago, right? This is Q over AB. So the flow rate, we found that a minute ago, that's 0.1314 cubic meters per second. The area of the basin, that's going to be pi r squared. So pi times half of the diameter squared. So we can find that value. So V0, we'll say that's going to be Q divided by 10.5 squared times pi. Okay. And notice we're calculating that using a Q that is in meters and seconds, so that our answer here is meters and seconds. And of course, our area also needs to be in meters units. That's all true, so we get an answer of 3.79 times 10 to the minus 4. Meters per second. Now our Vs was it 5.75? Times 10 to the minus fifth meters per second. And the answer would be no, it is not greater than or equal to V naught, right? It's, in fact, Vs is less than V naught. Okay, does that make sense? All right, so it's not overly complicated, but there's several moving parts in order to solve this one. You'll notice this one doesn't really have a direct mass balance, so we're not really getting to that just yet, but the mass balance will come when we add in coagulation to make these larger particles. So we'll talk about that shortly. Okay, in fact, we'll talk about that now. Okay, so I have another set of slides, which these are not the ones. Just a moment. There we go. Okay. All right. So we already talked about this. I guess I have slides slightly slightly out of order, but it doesn't matter whether it's circular or rectangular. Area of the basin is going to be the area of the basin, right? That's kind of the point of that problem we just did. And what's interesting is simply that it's that area of the basin that actually ends up mattering for our calculations. That's kind of the most important design parameter. In fact, one thing that you'll notice if you take a look at more coastal or environmental places where we find sedimentation, deltas are like sedimentation places or basins, because we've got sediment being carried out by a river, typically, and then suddenly the river has a lot more wider space to go, and so the water effectively slows down with a greater area for that basin, and you have particles settle. So why a delta forms is because of the same principle. There are a few other things to it. When we hit an ocean, we also change the salinity, as we'll see in a few minutes. That makes a big impact on particle stability as well. But even in a freshwater stream reaching a larger pond, you'll see a delta form where stuff that was in the water column is now dropping out because it's going at a slower pace. Okay, well, one question we might ask is how can we improve that sedimentation and make it more quick? Well, one thing we could do is to artificially increase the area of the basin by adding in shelves. Now, this is a little bit fancier and a little harder to accomplish in practice, so it's not used all over the place, but we can technically do a high rate settler by doing shelves. You're going to have to take a little more care when you're removing the particles. There's going to be a lot more maintenance. And how do you gather and collect all the particles safely and all that without taking them back up into the water column? There's several questions there that you kind of have to deal with. But you can do it, and then essentially what you're doing is you're just adding shelves. You can flow the same amount of water, and now the particles have less distance to travel. And the way we are seeing that increase the area of the basin, essentially, is by artificially adding in more layers of area of the basin, right? It's actually mathematically works out just that way. So if we have multiple sheets, now we went from one area of the basin to 4 area of the basins, right? 4AB is kind of our surface area now, right? 1, 2, 3, 4. So that's one pretty neat way to do it. Possible. Another thing we can do is use an upflow design. Now this one's a little strange. This is going to be, again, we're doing a cross-sectional view of this, so this might be circular. Doesn't have to be. But we're going to flow our water upwards and then harvest the water as it crosses over the rim of this basin, okay? So what's going to happen here is we're going to have velocity of the water, but it's going to slow down. Because this is shaped in this sort of trapezoidal manner, the water reaching the surface is going a little slower than it was when it entered towards the bottom. So we have kind of a smaller water vector. Now, we need a condition where the Vs has to be greater than that VW right as it's about to cross in order to have sedimentation. And theoretically, if it is greater, it's probably going to stay there just beneath, and we'll find some equilibrium, but then it'll probably meet other particles and stick to them and then get bigger and settle faster. So assuming that some of that's happening, anytime we have the settling velocity greater than that overflow velocity, in this case maybe V naught here, like that speed, VW here is V naught. We would call that the overflow velocity. Doesn't really matter. I'm just showing you this more for interest than anything else. Because we're not really going to deal with these, I don't think. But that's how you would design it. Anytime VS never reaches that, it's just going to escape. So it's kind of an all or nothing. So it's either 100% removal or 0% removal in this particular scenario. It might be pretty useful in certain industrial applications if you're just trying to sort particles by size, and to, maybe separate two different things from a stream of water. Certainly are some uses of it, and I've heard there are some cases in water or wastewater treatment. It's just not very common, kind of peculiar. And the fact that it's all or nothing is not super helpful in most cases. Okay, here's the slide I thought I was going to show you. We already covered this, but I'll just stop here just a moment to say, here it is again, nicely drawn. That percentage P, the percentage of particles removed, is Vs divided by V naught times 100%. This also means we can calculate, if we know some fraction that was removed, we can go back and calculate, oh, what's the design velocity then? Or, oh, what's the Vs if we had the design velocity? So we can use this to find, let's say, Vs if percent and V naught are known, right? So we can use this for a few different scenarios, right? Okay, if we removed 50% of particles with this condition, how big does a reactor need to be to remove this other one? Well, how big the reactor needs to be is caught up within the V naught equation. So we can go through and extract information from there. Okay, but we already covered that essentially, so we'll move on. Now, I've talked a little bit about coagulation. So where is this and where are we in a water treatment process train? Well, now we've covered the first sedimentation, and next up is to add a coagulant and give it time to do flocculation. So flocculation is the time where particles are allowed to meet one another and stick together. So coagulants are going to be the substances we use to make them sticky. So next up, we're going to talk about coagulation. We'll leave flocculation for next time. For coagulation in particular, we tend to it's like adding a chemical and mixing it up really fast to our system. So it's usually a pretty small chamber, rapidly mixed, just to get them together. And then we give them time in the flocculation chamber to let them slowly meet and particles to grow and all that. After we do both of those steps, then we'll go back to sedimentation again. Of course, we don't need to relearn all that, but we'll go through that step again in order to now make use of the better particle diameter, so the better settling velocity, get more removal. Okay? So all of this is piecing together to say, can we do simple things to make gravity work better, to make use of gravity, all that. Okay, so let's talk for a moment about what are we actually removing when we use sedimentation, and what is it going to require to, let's say, remove bacteria or viruses or things like that. So we have a particle size chart here for some things that some of them you should be pretty familiar with. You might look at rain droplets and say, oh, those are like a millimeter or less, right? So this here is 1 millimeter because this is micrometers, right? So 1,000 micrometers is 1 millimeter. If you get smaller than rain into like a mist or a fog, we are getting particles down to 100 micrometers, maybe even 10 micrometers, and a very fine fog all the way down to micrometer range. Pollen, there's of course very different sizes. The kind you normally see when it's like pollen season and everybody thinks it's like the worst thing in the world, it's usually the pines. They have really big pollen grains. So those are probably on this side of things. Most of what's allergenic is the smaller stuff that you can't really see so well, turns out, but you kind of know that they're there if you can see the pollen, right? Human hairs have a pretty wide range of sizes. You could see Most of them you can see with a visible eye, some maybe too fine, can't quite. You can see, actually there's that definition, the visible eye can typically see down to 10 micrometers at the very, very smallest. So you get a good understanding of that. Algae range from kind of the size of mist particles way down to smaller than a micrometer. And bacteria really don't typically get larger than a few micrometers. So usually they're around micrometer size. Thinking a moment back to the problem we just did, we were dealing with silt particles at the 10 micrometer range. That was 0.01 millimeters, right? So that was the size for the silt that we were talking about. And you could look at, this particular chart doesn't have it, but you can look at particle size charts for different types of soil, sand, clay, all that sort of stuff, right? So silt would be one example there. We also have different cysts, these cryptosporidium and giardia cysts. These are, you sometimes call them parasites. They're not like large parasites like a worm or something. They are still single-cell organisms, but they are eukaryotic, meaning they have a cell wall and they're a little bit larger cells than bacteria, but they kind of act like bacteria. So they're a little harder to remove with some disinfection technology, so it's nice if we can remove them with filtration and sedimentation. Okay, so given all that, from the example we worked, it's a pretty reasonable example, we noticed we were not able to remove these particles. So with basic sedimentation, we're looking at removing particles that are probably more like in this range or higher. Now, that means when we do more advanced, aka we add some coagulation, we're trying to make larger particles that kind of shift anything that we can to the right to make them larger. So hopefully some of the bacteria even might stick to a larger particle and be removed even right there before we even go into disinfection. Now, you'll notice viruses over here are really quite small. And there's no way they're going to sediment at all unless we can grab them with some other, with the coagulation stuff and stick them to a much larger particle. But they tend to be pretty stable in terms of not liking to stick to other stuff, and they tend to be very small, less than 100 nanometers. So this would be 100 nanometers here, just like this would be 1,000 nanometers, and so on. And so there's just no way they're going to sediment by gravity. In fact, if you ever work in a biology lab, you might grow bacteria and then centrifuge them to get a little pellet of bacteria. That's something that's not too uncommon. Well, if you try to do that with viruses, you would need a really, really fast centrifuge that puts a lot of G-force, because you have to artificially upgrade that G. In our equation we looked at, it's the G times the difference in density. Well, viruses are so small, you need a really, really large G factor to actually get sedimentation. And even then, you might wait half an hour at a really high rate centrifugation. So there you have it. That's kind of the gist of the types of things we might be interested in. And a lot of times it's actually growing particles, causing things to stick together that really helps us get productive removal. Okay, so that begs the question, what allows particles to not stick together? So what keeps them apart? So that's a question. If we answer that, then we can know what can allow them to stick together. Okay, so we'll just get a few minutes into this and then resume next time. So most of particle stability really has to do with electrostatic charge. So it's kind of like static electricity in a sense, where if you make a balloon really staticky, you can feel it's going to repel or attract different stuff. And even if you had like a stream of water and you had a charged balloon, you'll see it kind of pulls the water towards it. Or, you can see your hair standing on edge and things like that. So the electrostatic interactions in water kind of act like the particles stiff-arming each other if they have the same charge, which is relatively typical. So most particles in water tend to have a negative charge at the surface. So if these have a negative charge, what ends up happening is that charge is transmitted through water because other charged species, ions in solution, tend to gather near that charge and make what we call a double layer. So if the surface itself has some charge, then we'll end up attracting some positive charges, positive charge ions. So I'm going to put a little circle around them. Now, it's not going to be perfect, and some of these will have multiple charges, but in general, that first layer is almost all positively charged. Now, the second layer, this positive charged layer attracts negative charges, right? Kind of obvious. Now, we get a lot of entropy and diffusion and things, so it's the further we go out, definitely the more this becomes variable, and it's not going to just go forever, right? It's only going to go for some number of nanometers, actually. It's not a huge distance. So the next layer will be mostly negative to arrange itself, but there's also going to be some positives hanging around just randomly in solution, right? So with this double layer, we end up getting some repulsion. So this electrostatic charge, we have some surface and some other surface. That electrostatic charge will repel each other, right? So they're going to stay away from each other. Now, there's actually more forces like that, more forces than that can have some impact. And if you get close enough, those other forces tend to dominate. If you recall or think about like gravity or magnets, if you have two magnets and they're this far apart, there's a good chance they're not even really, you don't even feel any force between them, right? Likewise, if you were to go out into space and be pretty far from any planet, there's a good chance you're not feeling a strong gravitational pull. But if you get close enough, then that force becomes a lot stronger, and it's kind of like that force is decaying as a function of the radius away from the center, right? For gravity, for the magnets, you've seen that type of force before. So if electrostatic has a r² dependency, then these so-called van der Waals forces these tend to have something like a r to the 4th, or sometimes r to the 6th dependency. So these are strong forces, but you have to get very, very close. If you've ever watched some little bug walk on water, or some little bug crawl on the ceiling, or on like very, very clean looking glass, what they're using is van der Waals forces. They're getting the van der Waals forces for the water, that's like surface tension and things, and there's enough tension to resist the little leg, or on like a gecko or a frog on a very clean glass surface, they're actually getting their little sticky pads, their molecules close enough to that surface to make use of these van der Waals forces. So they're very attractive. They can attract very strongly, but they have to be very close. That's the deal. So all this really means is this is very close range. So the electrostatic repulsion tends to be the one that dominates because it keeps them at a further range. But if you can bridge that or eliminate that in some way, then you will get good potential for attraction there. Okay, so another way to kind of look at it, probably better drawing than mine. At some point you get to the bulk liquid, meaning it's just random. And until that point, next to the surface you have this electrical double layer, EDL. And this can have some distance out into solution, but that distance can be variable based on what kind of charges are around, how many charges of these are like 2 plus or 2 minus or 3 plus, 3 minus, those tend to compress it because they're taking up less space to accommodate that charge. Okay, so I think I'll resume there at this point next time to see what happens in practice when we do that. All right, like I said, I'll try to get that second homework up posted for you this week, and I'll see you Thursday.